Hey gang, welcome back. We're talking today about column buckling. I want to introduce that to you. What does that mean? What is that, what's involved here? And how do I find out how much load a column can handle before it fails, okay? So there's some things that we need to know about columns. Let's start off with number one, okay? And that is the difference between long column and short column. Now, number one, all the problems that you're going to see in your book are going to be long column because long columns buckle in a different way than short columns do. This is Yardstick, okay? This is what I consider a long column, okay? It's long, it's skinny, and when I mash on it, look how it buckles, okay? Now imagine my hand up here is a pin connection. It allows this thing to rotate freely on my hand, right? So when I mash on that, I get this buckling. Can you see it? Okay. That's a long column buckle. Now, what is a long column? A long column has a slenderness ratio. The slenderness ratio is the smallest dimension, which would be the thickness of my yardstick here, right? Not the width, but the thickness of it, divided into the length. And so how many times does this thickness go into the length? And if it goes, now the jury's out on this, like what's the slenderness rate? It's called the slenderness ratio, by the way. Okay. What is that number that the length gets divided into by the smallest diameter? Some say 12, some say 30. I think most people would agree it's 30 or above to be, and I've seen some that say 120, but 120 times into that thickness. But I think most of us say 30 times is the number for the slenderness ratio. So that is a long column. And like I said, all the problems that you're going to see in the book, all the problems that you're going to work out on your homework are all going to be long column. So if there's long column, there must be a short column. Yeah. Well, short column might be something like this Coke can, right? This Coke can is a short column because think about its dimension. Okay, how many times does the width here go into the height? Well, certainly not 30. It's maybe like 2, right? So short, fat column here, okay? Now, how does this buckle? Let's just test it out. I'm going to put it on the floor, and we'll put man-sized weight on it. I'm going to go really slow and see if I can actually stand on it empty. You think I can? Oh, I don't think I can. Now look how short columns fail. They don't bowl, right? They don't buckle. They crush. They collapse upon themselves. That's a short column failure. That's totally different than a long column failure. Now we know that. Okay. So, like I said, we're going to be dealing with long columns. Now, the next thing I need to know about long columns, and the next thing that makes a difference in buckling is how these ends are connected, right? If I'm pin connected, you can do this. If you have one of those little metal rulers, little 12-inch ruler, keep your hands open and buckle it and see how easy it is, okay? We call that pin. Each one of those ends is pinned. Now, these are called the end fixity conditions, okay? There's a new vocabulary word for you. The fixity conditions, how the ends are fixed, okay? If it's pin, we have this K value, which is the end fixity condition, right, of 1. Now, this is also called the ideal condition, okay? So pin is ideal. And ideal means it's equal to 1. And I'll show you what happens when we have that a little later on. Now, go to number 2, fixed. Okay, now fixed, we know what fixed is, a fixed support, right? Like a cantilever beam. Now, I want you to grab your little ruler and make a fist on both ends, right? Now it's fixed. I'm not going to allow the ends to rotate. It'll still buckle, but mash it together now. Don't let the ends rotate. I can't do it. It takes a lot more force because now when this thing buckles, before when it buckled like this, okay? But now with the ends fixed, it might buckle something like this, okay? It still buckle, but the ends won't, okay? This takes, and you can do it with your hand. I've got a dent in my hand. Thank you very much. Takes a considerable amount of force to buckle it with this end condition versus that one, okay? So the K value goes to 0.5 on that one. Now, pin fixed means that one end is free to rotate. The other end is fixed, so it's kind of in the middle of those two. It's kind of a hybrid connection. The K value for that is 0.7. And then there's fixed free, which is like a telephone pole, right? Now, it has a wire hook to the top of it, so it can bow, it can buckle, right? Also, and the K value for fixed free it's the easiest to buckle of all of those kinds. K value is 2 on that, okay? Now, where in the heck are we going to use this K value, okay? When we're talking about buckling, one of the main things that we want to know is this. What is that critical force, right, that when I compress that system is going to make that column buckle, is going to make it fail, okay? And what we do on that is we use this. We use Euler's buckling equation. It's not Euler. Don't say that wrong, okay? I want you to look really good in front of everybody else. Say Euler, because he's like, he would be mad if you mispronounced his name. This is the buckling equation. P critical equals pi squared E, that's modulus elasticity, right? That tells us about the bendiness of the material, times I is area moment of inertia. That tells us about the geometric properties of the cross-section. Is it a diving board or is it an I-beam, right? And then down here on the bottom, now this is where I see most of the mistakes on this made, is right there with that K value. That K is inside the parentheses. Now, a lot of these times you'll see this equation and you'll see it written in the ideal form, which means K is 1, and so you won't see that K there, and you'll just see L squared. And so then when you do put a K in there, I see a lot of people that say, oh, the K must go outside. No, it's quantity squared. The K is inside the parentheses, okay? So don't mess that up. Depending on what your end conditions are, that multiplies times the free length. This L right here is the unsupported free length. This beam didn't have anything in the middle of it. If it would have been pin connected in the middle, then the free length would have been from one end to the middle where it's supported, right? So this L is not just the overall length of the beam, it's the free length of the beam, the unsupported length of the beam. That's important, okay? Now, the two things that I see messed up, number one, getting the wrong end fixity conditions. And we're going to do an example problem. Next video, watch that. The end fixity conditions change depending on the direction you look at the problem. Check that out, okay? That's number one mistake I see. And number two is this, I can be confusing, okay? Because let's look, for instance, at this problem here, okay? Find the critical buckling force for the 10-foot long column. Assume pin-pin ideal connections, right? So I've just got what we would call an I-beam. Okay, question of the day. Why do we call it an I-beam? I know what you're saying right now. Because it looks like an eye. Okay, smarty. Okay, smarty. How about this? Here's same beam. Okay, here's same beam. How come we don't call it an H-beam? How can we call it an I-beam? I'm going to tell you why, okay? Now, when we're talking about bending or buckling, okay, we have this guy here, a neutral axis, okay? And if you remember remember when we discussed I when we first came up with it? The farther away that I can get the centroid of half the part, let's say half the part would be like this guy right here, the blue here, okay? This part right here, okay? The farther I can get the centroid of that, here's the same thing over here, okay, in the I configuration, is that much, right? The farther I can get the centroid of this shape away from the neutral axis, the less likely it is to bend, right? The stronger it's going to be in bending. Well, in this configuration, the centroid of this may be like right there, right? So this distance right here is not very far, if we're going to call that D. It's not very far away. Whereas over here, I've got all of this area which brings that centroid maybe to like there, right? Same shape, but look how big D is now compared to that. So if you have a column, it is always going to fail in what we call the weak axis. This is the strong axis. This is the weak axis of bending. Okay? So it's always going to fail around the weak axis. And that's why we call this an I-beam and not an H-beam, because it's strongest in the I direction. If you go on a job site and you see somebody putting a beam up and they're welding it horizontally, let's say, and they got it in the H direction, you need to go up there and tap them on the shoulder and say, hey, you're installing that wrong. It's not strong that way, okay? It's not. If you ever mess with an I-beam, it'll sag, it'll bend if you pick it up like this versus picking it up like that, okay? Now let's just demonstrate that real quick, okay? Let's just do this little trick. All right, let's try this. IX. This also is going to be IX, right? But it's completely different. Like what used to be the base here is the height over here, and what used to be the height here is now the base over there, okay? Let's see if we can do this. Now we're going to have to use, I think we're going to have to use the parallel axis theorem, okay? Which is going to be 1/12. Now on this one, right, what I'm going to do on this one, I think I'll do the whole thing and then subtract out these two windows here. How about that, okay? So 1/12, the base, which is 12, right, times the height, which the whole thing is 12, cubed, minus the windows. Oh, let's see. How big is that? Oh, this is 1 inch right here. Okay. So this is 10 inches by 11 inches, right? So 110 inches. What are you doing? This is AD squared. Remember parallel axis theorem? AD squared, right? No parallel axis theorem this time. Because where's the centroid of these pieces? The windows, the centroid is on, so D is 0, isn't it? So we don't need the parallel axis theorem. We got smudgies. Smudgies! Okay. So minus the windows. 1/12. The base of the windows is 11. The height of the windows is 10. Okay. Cubed. So here we go. That is equal to, what is that? Hey, check this out. We got 12 on the bottom and 12 on the top. So that's 12 cubed, 1728 minus, what is that? 10 cubed equals times 11. Divided by 12 equals 916.67. And so 1728 minus 916.67 is 811.33. And that's inches to the fourth. Let's do this one over here. Okay. This one I probably am going to have to use the parallel axis theorem, right? Because I've got to subtract out these windows here now, right? So let's just do, oh my goodness. Okay, I'm going to do the same thing, whole square minus the other part. Okay, so the whole square is 1/12, the base is 12, the height is 12, cubed minus, and here comes the next part, right, is these guys. There's two of them. Okay, and I'm going to do this, giant parentheses. And here we go. One of those guys is this. The 1/12, the base is 10, right? The height is, let's see, this height here is 6. That's 1, so that's a half. So the height is 5.5, 5.5. BH cubed minus A, that area, 5.5 times 10, that's 55. Times D. And remember, D is from the neutral axis to the center of that thing, right? So if that's 5.5, half of, let's see, what is half of 5.5? 5.5 divided by 2. 2.75. So it's 2.75, but that's here. And then I got to add a half to that, right? So plus 0.5. So that centroid lives at 3.25 squared. Okay? Now how much is that? Okay, this is 1728 again. That's what that is. And then what is all of that business? 1728 minus 2 times, okay, here we go, 5.5 cubed equals times 10 equals divided by 12 equals 138.64 minus 3.25 squared times 55 equals 580. Okay, and that's 580.9. Now wait a minute, 138, that's not minus, is it? It's plus 80 squared. Not oh, that was almost bad, wasn't it? So plus 138.64 equals times 2 equals 1439. This part right here is 1439.15. Subtract it off of that, so 1728 minus answer is 288.8. Okay? So, the moment of inertia, look, it's a lot smaller than that is, isn't it? Okay? So it's going to fail in that direction, not in this direction. This is the strong axis, weak axis. Now check this out. Pi, never going to change. E, the material, I don't care which configuration, that doesn't change. I, that does change, right? And then K, of course, the end conditions can change. The free length here is 10 feet. So I think we have everything we need to calculate the critical force. Let's do it. P critical for this particular column is equal to pi squared times E, which is given as 29 times 10 to the 3 K, which is Kips per inch squared, right? Units, we got to get all our units to work out. Now we're going to use this I times 288.8 inches to the 4th divided by, okay, now this is pen, so our K value here is going to be 1. And then, of course, our length is 10 feet. What are we going to do with that? Multiply it by 12, 120 inches, okay? And then we're going to what? We got to square that, don't we? Okay? All right. And guess what? The inches squared, that one goes to the bottom. I got another inches squared, going to cancel out with that inches to the 4th. Going to leave us with P in Kips, isn't it? Let's see what we get, gang. Here we go. 3.14159 squared times 29, 1, 2, 3,000 times 288.8 equals divided by 120 squared equals, bam, 5,740 Kips. Okay? Now remember, a kip is 1,000 pounds, so we're talking about a lot of weight, aren't we? But that's a 12-inch beam, or I-beam with 1-inch flanges. That dude is going to carry some weight now. Okay? So there you go. That's how you use Euler's buckling equation. Like I said, the most missed thing is miscalculation. Which eye do I choose? Okay? Which eye do I choose? Well, it depends on which way it's buckling. And then, or which way you're going to calculate. This one, we're going to choose the weak because that's how it's going to fail first. And then, which K do I choose? What are my end conditions? So what's that next video? There's one that kind of, the end conditions change depending on which way you're looking at it. So that can be tricky. All right, I hope this is a good introduction to column buckling. I hope this helps, and I'll see you on the next video.